We are diving deep into the very heart of chemical change today.
We really are. We're talking about how energy moves, how systems find their balance.
And maybe most fascinatingly, why that balance is often just, one small push away from complete unexpected chaos.
Right. So our mission for this deep dive is to take a stack of sources that starts with something as simple as the heat in your coffee cup.
And connect it all the way to some pretty advanced theoretical physics. We're trying to connect the dots between classical chemistry and, well, the new rules that govern these dynamic systems.
And that's the core challenge, really. We're looking at a set of universal rules that apply whether you're, I don't know, burning a log or freezing water.
At the most basic level, all chemical change is governed by energy transfer. And here, the sources are crystal clear. You've got exothermic reactions.
The ones that release energy, yeah. And then you have endothermic reactions, which absorb it.
And to make that distinction really stick, the source material gives us this classic demonstration from Daniel Rosenberg. He mixes two simple solids, barium hydroxide and ammonium chloride.
And the reaction that happens just absorbs so much heat from everything around it.
That it literally freezes a puddle of water, sticking the beaker right to the table. It's an incredible visual.
Oh, absolutely. That beaker, stuck solid to a block of wood, is just the perfect image of an endothermic process. The system, the reaction mix, is soaking up all the thermal energy it can from the surroundings.
And the opposite of that, the exothermic process, that's just striking a match.
Exactly. The chemical energy that was stored in the wood gets converted into light and heat and, released into the room.
So we know from the first law of thermodynamics that energy is conserved. It's only ever converted or transferred. But in chemistry, especially when we're talking about reactions happening out in the open, we don't just say energy.
No, we don't.
We use the term enthalpy with a capital H. Why is that specific distinction so crucial for chemists?
It really comes down to practicality and precision.
Mm.
Energy as a total measure, that's E, includes all the internal energy. But when you're running a reaction on a lab bench,
Right, just out in the open.
it's happening under constant atmospheric pressure. So enthalpy, which is defined as H equals E plus PV energy plus pressure times volume. It accounts for the heat that comes in or out and also the work done by any pressure changes.
So because the pressure is constant on that lab bench, that whole pressure volume work term, it mostly just drops out.
Exactly. So for chemists working in standard conditions, the change in enthalpy, delta H, effectively becomes a direct measurement of the heat transferred, which we call Q. It just simplifies the math so much.
So if delta H is negative, heat is released. That's exothermic.
And if delta H is positive, heat is absorbed. That's your endothermic reaction.
Okay, so if we're looking at the energetics, an exothermic reaction is kind of moving downhill. If the system releases heat, does that mean the bonds in the products are actually stronger than the bonds in the reactants? That feels a little counterintuitive.
It's a great question, and one that really trips people up. Think of it like this. The reactants hold a certain amount of potential energy in their weaker bonds. You need a little energy input to break those bonds. But then, when the new, stronger product bonds form, they release more energy than you needed to break the old one.
Ah, so it's the net energy released by forming those new superstable bonds that heats up the room.
Precisely. That's why combustion is so effective. Take methane, CH4. Its combustion releases a massive 890.4 kilojoules of heat for every mole. The system is just moving to a more stable, lower energy state, and that extra energy is given off to the surroundings.
And the reverse, endothermic, means the products actually require more energy to hold their bonds together, so the system has to steal that energy from its environment.
Yeah, like to decompose calcium carbonate, it has to absorb 177.8 kilojoules per mole.
So that sets the foundation for energy flow. But most reactions don't just go one way, do they? They eventually reach a state of balance, chemical equilibrium.
And the sources are really careful to define this not as some static stop state, but as a dynamic balance.
What does that mean, dynamic?
That's the essential part. At equilibrium, the rate of the forward reaction perfectly matches the rate of the reverse reaction. So the concentrations look constant, but underneath,
Molecules are still reacting?
constantly, they're breaking and reforming all the time. This stable, constant ratio of products to reactants is what we define mathematically with the equilibrium constant K.
And if you mess with that ratio, you trigger this. Well, this elegant principle of chemical self-correction. The Chatelier's principle.
The Chatellier's principle, or LCP, just states that if you disturb a system that's at equilibrium, the system will shift its reaction rates to directly counteract whatever you just did.
Like negative feedback.
It's pure negative feedback in action. If you increase the concentration of a reactant, the system shifts to consume it and make more product.
And the mechanism behind that is just straightforward collision theory, right? If you dump in more reactant, you're just increasing the chances of successful collisions.
You are, yeah, which temporarily boosts the forward rate. Now, the second big lever you can pull is pressure.
But that only affects reactions with gases.
Right, and specifically where the number of moles of gas changes. If you increase the pressure, you push the equilibrium toward the side with fewer moles of gas, because the system wants to reduce that overall pressure.
The industrial application of that is huge. I'm thinking of the Haber process making ammonia for fertilizers.
The perfect example.
You have 1 mole of nitrogen plus 3 moles of hydrogen, so 4 moles of gas, reacting to produce just 2 moles of ammonia.
So to maximize the ammonia you get, manufacturers just crank up the pressure. It forces the equilibrium to shift to the right, toward the side, with the lower mole count. The system is literally fighting the pressure you're applying by making fewer gas molecules.
Okay, but I remember a tricky part in the source material here. What if you add an inert gas, like argon, to the mix? That increases the total pressure, so why doesn't LCP predict a shift?
Ah, that's where the details really matter. If you add that inert gas while keeping the total volume constant,
Okay.
the total pressure goes up, sure, but the partial pressures of the actual reacting gases, the nitrogen, the hydrogen, the ammonia, they don't change at all. And since the reaction rate depends on their partial pressures, the equilibrium position is completely untouched.
No counteraction is needed. Okay, that makes sense. Let's move to the last major lever, temperature. If we increase the temperature, LCP treats heat as either a reactant or a product, depending on the delta H.
Right, so increasing the temperature will always favor the direction that consumes that added heat.
Which is always the endothermic direction.
Always. So if you have an exothermic reaction, adding heat actually pushes it backward. If it's endothermic, adding heat pushes it forward. This is how engineers optimize for yield versus energy cost.
And this brings us to a really crucial point about LCP. Changes in pressure or concentration, they just shift the position of the equilibrium to get K back to its original value.
But temperature,
Temperature is the real disruptor.
it's the game changer. Temperature is the only variable that fundamentally changes the numerical value of K itself. The math behind this is laid out in the Van Hoff equation, which links that temperature change directly back to the reaction's enthalpy.
So it's the formal link between the heat flow we started with and the final state of balance.
It ties it all together.
Okay, before we dive into the really deep theory, let's ground this with some applications. LCP isn't just for huge industrial plants. It dictates simple things like solubility.
Which leads directly to something called the common ion effect.
Right, so when an ionic compound dissolves, it dissociates into ions. In a solubility equilibrium, you have a solid on one side and dissolved ions on the other.
Okay, so if you add a different soluble compound that happens to share an ion with that solid precipitate, the common ion, you're effectively adding a product to the right side of the equilibrium.
And LCP demands this system counteract that?
Precisely. It shifts the equilibrium back toward the solid form, which means the solubility of your original compound actually decreases.
The sources mention a fantastic real-world use for this: water treatment. Hard water is full of dissolved calcium ions.
So by adding sodium carbonate, you introduce a ton of extra carbonate ions.
And that carbonate is the common ion, which forces the sparingly soluble calcium carbonate to precipitate out of the water.
And just like that, you've softened the water by removing the dissolved calcium. It's a very clever use of LCP.
Shifting gears from solutions to actually measuring this stuff, we use calorimetry to quantify that all-important enthalpy change.
Yeah, even simple foam coffee cups can be used as makeshift calorimeters in a high school lab to minimize heat loss.
But for really precise measurements, especially for things designed to be burned, like fuels, scientists use something else.
You're talking about bomb calorimetry.
Exactly. I was really fascinated by the work of Gretchen Sassenrath, who used this to study potential alternative biofuels.
Yes, looking at high-energy crops, like sweet potatoes of all things. We usually just see them as food, but her team measured the energy locked away in the plant residues.
And to do that, they used a bomb calorimeter. It's the sealed high-pressure vessel. They incinerated the material inside and measured the exact heat that was released.
And the number they got for sweet potato was pretty high, 1 gram contained 3,966 chemistry calories.
And this is where we have to clarify the scale for everyone because the word calorie gets so confusing.
It's a critical clarification. One food calorie, with a capital C on the nutrition label, is actually 1,000 chemistry calories with a lowercase c.
So that sweet potato data translates to almost 4 food calories per gram.
Right. And their research suggested that, on a per-acre basis, these energy-dense sweet potatoes could yield more energy than several traditional ethanol crops. They're a serious contender for sustainable biofuel, and we know that thanks to a precise delta H measurement.
Now let's take that concept of equilibrium valence, of K, and apply it to giant biological systems. Let's introduce the dissociation constant, or Katie-Dahl.
Katie-Dahlers is essentially the equilibrium constant for the separation of a large complex, usually a protein binding to another molecule, which we call a ligand.
It measures how likely that complex is to break apart.
Exactly. It's the inverse of the association constant.
And this is absolutely fundamental to pharmacology. A drug's effectiveness is often all about its affinity for its target. So a good drug needs a low K-Dahlor.
Precisely. A low K-Dahlor means high affinity. The drug binds tightly and it stays bound. Mathematically, K-Dahlor has this really neat property. It's equal to the ligand concentration you need to occupy exactly half of your total target protein molecules.
So if you only need a tiny amount of the drug to stick to half the receptors, you've got a great drug.
Yeah.
And the sources gave a spectacular factoid about just how strong some of these biological bonds can be.
Oh, yeah. The binding between the protein avidin and the vitamin biotin. It's legendary in molecular biology.
How strong is it?
They bind with a sub-picomolar dissociation constant. That's around 10 to the minus 15th molar. To put that in perspective, people sometimes call it nature's strongest non-covalent interaction.
Wow.
It just shows how incredibly stable and strong an equilibrium can be, even inside a fluid living system.
Okay. We've established this stable, predictable world of classical chemistry enthalpy, KLCP. But now we have to signal a major conceptual gear shift. Because that classical framework, as useful as it is, it often breaks down when systems are open or far from equilibrium. We are now diving into the thermodynamic theory of chaos.
Right. Traditional thermodynamics handles isolated systems beautifully. Systems that don't exchange energy or matter with their surroundings. That's what we call true thermodynamic equilibrium, or TDE.
But the real world isn't isolated.
Not at all. The moment you look at a living cell, or even just an open-air reaction that's constantly exchanging heat and gas, the traditional models struggle to predict what's going to happen because these are open systems.
So this new theory, which comes from researchers studying the boundaries of these systems, it tries to unify that stable, isolated world with the unstable, open world. How do they reframe the core idea of equilibrium?
They stop looking at it as just a balance of forward and reverse rates. Instead, they view it as a balance between thermodynamic forces. They introduce this idea that the system has an internal stabilizing force, which they call eugen affinity.
Eugen affinity. Wait, can we unpack that term? Is it sort of like a chemical inertia?
That's a really good analogy, yeah. Think of eugen affinity as the system's own intrinsic desire or tendency to maintain its current composition. It's the inherent stability of the system pushing back against external changes.
Okay, so you've got the system's desire for stability, its eugen affinity, versus all these disruptive forces from the outside world. And this balance is formalized with a mathematical model, a logistic equation that defines a system's domain of states. What are these states?
The domain is a spectrum of stability. On one end, you have TDE, true thermodynamic equilibrium, where any deviation from balance is zero. It's a perfectly still pond. Next is open equilibrium, or OPE. This system is open. It's exchanging energy and mass, but it finds a single, stable operating point. It's like a river with a constant, steady current. It's flowing, but it's predictable.
But the theory doesn't stop at stable flow. It moves into the unpredictable.
Exactly. Beyond OPE, the system can enter bifurcations. Here, multiple stable states become possible. A small push could send the system down one path or another, like a fork in that stable river. And finally, you have chaos.
A waterfall?
A waterfall. The system becomes utterly sensitive to initial conditions. Even the tiniest external force causes huge, unpredictable changes.
So that means even simple chemical reactions aren't guaranteed to be in that stable state. They could be balancing on the edge of chaos depending on how we treat them. What parameter tells us where on that spectrum pond, river, fork, or waterfall a system actually is?
That is the powerful innovation here. It's the reduced chaotic temperature, symbolized by Taj. It's a new dimensionless parameter that controls this whole stability landscape. The size of this number tells you where the system falls in its domain of states.
And what is it? What does it measure?
It's a ratio. The numerator is proportional to the external forces acting on the system, and the denominator is proportional to the system's internal resistance. It's Eugen affinity.
So if the external impact is high compared to the system's ability to resist, Tage increases, pushing the system away from that stable equilibrium and toward bifurcation and chaos.
That is the key mechanism. And this theory, it elevates the whole discussion back to the most fundamental driver of all change, entropy.
Right.
Classical models relied on Gibbs free energy, a property of the system itself, to predict spontaneity. This new view reiterates that the change in the total entropy of the universe, so the system plus its surroundings, is the true origin of all change. Gibbs free energy is, in this light, just a contrived or subsidiary property of the system.
Wow. That is a profound shift in perspective. We started with simple heat transfer and the need for enthalpy to keep track of energy on a lab bench. Then we moved through the pragmatic predictability of Le Chatelier's principle, applying it everywhere from industrial synthesis to water purification and biofuel evaluation.
And we finished by challenging the very idea of chemical stability, moving from the dynamic balance of K and Kitty D to the theoretical edge where classical thermodynamics meets chaos theory. It's all governed by that balance between internal Eugen affinity and external forces.
So it's clear that stability isn't just a given, it's an actively maintained state.
Absolutely. The discovery of this reduced chaotic temperature, Tauge, shows that every chemical system, no matter how simple it seems, has this built-in sensitivity to its environment, which leads us to a really provocative thought to end on.
Let's hear it.
Considering the high sensitivity of biological and pharmacological systems, where drug binding is defined by these tiny differences in kD dolars, if these systems are constantly balancing on a knife edge defined by this tau J parameter, how often might a small, common external disturbance push a seemingly stable biological process, or even a critical drug interaction, into a catastrophic domain of bifurcation or chaos?